I should also say that the news yesterday was that this object came closest to the sun, and it received a huge amount of heat from the sun. And the latest report indicates that it became extremely bright, much more than expected for familiar comets. This morning, we have a report that the object got much brighter than expected, and moreover, the color of the object is blue, bluer than the sun. And that's very surprising, because usually when there is dust around an object, it should make it red.
The interstellar traveler known as 3I Atlas has jolted the scientific world by performing what observers are calling a deliberate braking maneuver, a behavior no previously studied comet or asteroid has ever displayed. NASA's Jet Propulsion Laboratory reports measurable deceleration relative to the sun's pull, with non-gravitational acceleration components that don't fit a purely passive natural body. Before we dive in, if you enjoy deep space mysteries told clearly and calmly, tap like and subscribe for more. The first alarm rang when astronomers realized 3I Atlas's velocity didn't match a simple hyperbolic flyby. Its motion appeared to slow, as if brakes had been applied, and its path began to deviate from a purely gravitational arc. Recorded values pointed to a radial acceleration of roughly 135 km superscript 2 from the Sun and a transverse component near 60 km superscript 2. Figures that, in context, are hard to square with sunlight and outgassing alone. At discovery, 3I Atlas already looked interstellar, inbound on a hyperbolic trajectory, moving faster than typical solar system comets, arriving from beyond the sun's dominion. But recent monitoring has revealed a chain of subtle, profound anomalies. At times, its tail structure appeared to reverse, pointing toward the sun, unusual for standard comets, whose dust and gas are usually pushed away by radiation pressure. The reported braking event is especially compelling because it implies an active process, not just passive physics. The idea of an object slowing down, engaging in what looks like controlled deceleration, raises unsettling questions about its nature and origin. Could this point to artificial propulsion or a form of engineered maneuvering? NASA's language, non-gravitational acceleration, means conventional forces like solar wind or ordinary outgassing don't fully explain what's being seen. Consider the mechanics. An object passing through the inner solar system faces a predictable set of forces: the sun's gravity, perturbations from planets, photon pressure, and perhaps outgassing if ice is sublimate. These yield characteristic signatures. But when acceleration components don't align with expectations, when a transverse push appears unrelated to simple radial infall, scientists must at least entertain the possibility of active control. In the case of 3I Atlas, the precision of the deceleration looks suspiciously deliberate. If confirmed, the implications are sweeping. Until now, interstellar visitors like 1I Oumuamua and 2I Borisov were studied as natural remnants from other star systems, passive drifters. But if 3I Atlas is actively maneuvering, we have to ask, are we watching probes or a construct from beyond our system? Or have we stumbled onto a new class of natural phenomenon unlike anything we've cataloged? Caution remains the rule. No one is declaring 3I Atlas artificial. Yet the wording and the magnitude of the anomalies have prompted serious scrutiny. One camp argues that outgassing can yield irregular motion. In this case, however, the directionality looks off, and the magnitude high enough to suggest more than a spontaneous vent of gas. The picture is less random jet and more vectoring. Imagine watching an object swing past the sun and then slow, as though tapping thrusters or unfurling drag. That is the scenario emerging. The braking is not simply a speed drop from radiation or dust drag. The trajectory appears tuned, like a control maneuver. This defies the assumptions we've held about interstellar comets. Location matters. The braking was detected around 203 million kilometers from the Sun, just inside Mars's orbit, a region where solar forces are still significant but not overwhelming. An active intervention here would require energy, precision, and timing. That distance suggests navigation, not a wayward stone simply bullied by gravity and wind. If one accepts, even hypothetically, that 3I Atlas performed an artificial maneuver, the possibilities become breathtaking. A probe from another star, a relic of an alien civilization, a vehicle repositioning to linger, adjust its exit vector, or redirect toward target region. Even without that leap, the event forces a shift in mindset. Comet science has long centered on sublimation and solar wind. The notion that an interstellar object could thrust or break pushes astronomy and astrobiology into new territory. There are practical stakes. For planetary defense, mission planning, and interstellar reconnaissance, this demands new protocols. Observatories must treat interstellar objects not just as curiosities, but as potential artifacts of motion and intention. The ability to detect minute deviations in acceleration becomes crucial. The breaking of 3I Atlas functions like a technosignature, a candidate marker of engineering, requiring rigorous verification, multiple platforms, and continuous tracking. What would breaking accomplish? One possibility is a trajectory change. Instead of a clean sweep through the system, a slowdown could enable an Oberth-like maneuver, leveraging the sun's gravity well, pushing or braking to redirect. Another is station keeping near the inner solar system to observe, sample, or simply extend dwell time. The earlier sunward plume could even align with a deceleration process, jets directed toward the sun to bleed speed. Whatever happens next, 3I Atlas will ultimately depart, sliding back into interstellar space. If the braking is confirmed as artificial, it would be the first observed artifact of extraterrestrial motion by engineered means, an epical moment. Even if a natural mechanism emerges, this case forces us to refine detection, revise classifications, and raise our readiness for future visitors. Right now, teams are coordinating telescopes, expanding data pipelines, and stress-testing computational models to decode 3I Atlas's motion. They're dissecting the light curve, tail morphology, dust and gas emissions, and acceleration vectors. If any thrusting exists, its fingerprints could appear in asymmetric dust ejection, localized jets, or sudden attitude shifts. The braking event becomes a prime case study, a testbed for distinguishing the natural from the artificial. At a deeper level, this brushes one of humanity's oldest questions. Are we alone? If an object from another star passes through our neighborhood and slows intentionally, perhaps to observe, perhaps to bypass, we confront the tangible possibility of contact, not as lights in the sky, but as engineering in motion. It recasts us as watchers of traffic, not passive recipients of debris. It also challenges our sense of agency in space. Most celestial bodies drift, orbit, or tumble without intent. Here is a body that seems to exercise intent, or have intent exercised upon it. Braking implies foresight, calculation, directionality. Whether that belongs to a civilization or to unknown natural forces operating under conditions we don't yet grasp, the fact remains, this object is not behaving like anything our system has seen. For mission designers, there's a curious thrill and a hint of dread in tracking 3I Atlas's path. They're probing for windows, signatures, or behavioral modes that could guide intercept strategies. Suppose an object slows near perihelion to reshape its exit. Our spacecraft sometimes do similar things, but we haven't seen interstellar guests do it. If a slowdown near the sun allows a new outbound vector, understanding that mechanism becomes critical for future campaigns. Composition adds intrigue. Some observations hinted at unusual chemical signatures, compounds not commonly seen in familiar comets. While data are preliminary, the combination of odd chemistry and braking deepens the mystery. It's tempting to cast 3I Atlas as a messenger or scout, but scientists remain appropriately cautious. Extraordinary claims require extraordinary evidence. Natural models are still on the table. Could the sublimation of exotic ices, strong jets, or mineral phase transitions near the sun account for the deceleration? Could radiation pressure acting on an asymmetric shape mimic braking? Possible, but the data lean toward motion that defies simple natural mechanics. In truth, 3I Atlas sits at the interface of astronomy, engineering, and philosophy. It tests our assumptions about natural motion, challenges how we flag oddities, and asks us to stay open to non-natural behavior. Even if this visitor proves purely natural yet exotic, the lesson will ripple outward. More careful observation, more deliberate caution, a broader taxonomy for interstellar objects. As ground observatories, space telescopes, and deep space probes continue to monitor 3I Atlas, they'll scrutinize its tail evolution, dust and gas production, and speed profile. The braking event stands out not just for what it is, but for what it could represent, a turning point in how we perceive alien arrivals. No longer distant points of light, interstellar visitors become actors, moving with intention, shaping trajectories, perhaps even expressing purpose. In a sense, the braking of 3I Atlas reads like cosmic punctuation, a pause, a measured slowdown in a clockwork ruled by gravity and sunlight. It is the moment when a traveler from the dark seems to choose, to adjust, to linger, to redirect. That possibility will change how we search, watch, and interpret future trespassers from stars. There is a further, sobering reflection on technology itself. If artifacts can traverse interstellar distances and then decelerate within a system like ours, they must carry architectures, materials, and energy systems beyond our present capabilities. The braking hints that technology may be embedded in the traveler, and that its behavior, braking, turning, vector shifting, could be as telling as its chemistry or tail. The analysis of 3I Atlas will likely seed new frameworks. Models of engineered interstellar objects may graduate from speculation to testable hypotheses. Survey programs will prioritize non-gravitational acceleration as a top-tier flag. The braking of this object becomes a reference point. Deviations from expected paths, unexplained pushes, tail anomalies, odd material signatures, controlled-looking deceleration near massive bodies. The sky is vast. Most motion is subtle. This object did not simply drift. It appeared to apply brakes. That suggests agency. It invites interpretation. It demands scrutiny. Whether the braking proves to be an alien engine, a natural oddity, or something else entirely, the effect is the same. Our perspective on interstellar visitors has shifted. We must now treat them as possible voyagers. As humanity looks outward, building telescopes, sending probes, deciphering faint signatures, the case of 3I Atlas underscores the need for readiness. When a next interstellar visitor appears, the first question may not be what is it made of, but is it steering? Braking offers one of the first clear markers to ask that question with rigor. The arrival of 3I Atlas delivered more than the thrill of a visitor. It delivered the possibility of sophisticated behavior. Its journey has compelled us to reconsider the categories by which we classify celestial wanderers and to bridge the gap between natural phenomena and potentially engineered objects. From the moment of discovery, 3I Atlas presented as the third confirmed interstellar guest after Oumuamua and Borisov. Its hyperbolic path signaled it wasn't bound to the sun. Speed and approach angle set the stage for surprises. Beyond that, deeper clues emerged: composition, age, environment of formation, hinting this was far more than a casual pass. Spectroscopy and infrared observations revealed an ice-rich nucleus wrapped in a CO2-dominated coma, with relatively less water vapor than expected for typical local comets. One study noted that at about $3.32 inbound, the CO2-to ratio was unusually high, suggesting formation in a colder, more distant region of its parent system, perhaps near or beyond the CO2 snowline. Data paired with SphereX analyses hint at an old, well-processed body that spent immense time in interstellar space. Some age estimates even place 3I Atlas as older than the solar system, implying billions of years adrift before our sun entered its story. Dynamics modeled with Gaia stellar data suggest an origin in the thin disk of the Milky Way, likely ejected long ago by gravitational interactions, perhaps with a giant planet or binary star, and flung into the void until it arrived here. In that light, 3I Atlas becomes not a mischance, but a rare archaeological sample from another planetary system. Sizing remains tricky. Early Hubble limits suggest an upper nucleus size around 3.5 to 5.6 kilometers, complicated by a dusty coma. Other observatories proposed 11 kilometer. Meanwhile, polarimetry reported an unusually deep, narrow negative polarization branch in the reflected light from the coma, behavior atypical of solar system comets, but reminiscent of some trans-Neptunian objects and centaurs. It hints that 3I Atlas may represent a class we haven't cataloged locally. Trajectory details add texture. Approaching from the direction of Sagittarius, its orbital plane lies near the ecliptic, making the passage unusually neat. It passed near Mars on October 3rd, 2025 at roughly 0.01935 Australian dollars, then reached perihelion on or about October 29th, 2025 at $1.36. After perihelion, it's due to depart, and yet its departure seems anything but passive. During and after perihelion, reports gathered subtle color changes, measurable non-gravitational components, unusual tail and plume structures. Observers documented a radial acceleration away from the Sun near 135 km superscript 2 and a transverse component around 60 km superscript 2. Values whose orientation is difficult to reconcile with simple radiation pressure or standard jets. Some argue enhanced outgassing could still fit, especially given high CO2 and dust-rich jets, but others point out that if gas jets drive this, we'd expect mass loss signatures, dense plumes, debris clouds, on a scale not clearly detected. One analysis even places an upper limit on non-gravitational acceleration near 3 times 1 superscript 1 Auto superscript 2, deriving a lower bound on nucleus mass around 3 times 10 superscript 1 g and a diameter floor near 5 kilometers, consistent with earlier estimates. The tension between theory and observation is precisely where the controlled deceleration hypothesis gains traction. Tail morphology deepens the puzzle. Conventional comets cast their tails anti-solar. Yet, 3I Atlas showed a sun-facing plume early on, an elongation toward the sun seen in mid-year observations, often interpreted as a distinct dust jet rather than a classical tail. As it neared the sun, a more familiar anti-solar tail developed and grew, but the earlier sunward feature remains provocative. Unsurprisingly, the artificial origin hypothesis has surfaced. Most astronomers still regard 3I Atlas as natural, rendered extraordinary by its age and chemistry. A smaller, vocal group has suggested the anomalies could be consistent with a probe or artifact, noting that the non-gravitational pushes don't perfectly align with outgassing models, that the trajectory's planetary proximities feel statistically odd, and that abrupt color shifts plus breaking echo internal control. Critics counsel patience. Comets can surprise us, and with new interstellar classes, we should resist the extraordinary explanation until the evidence is equally extraordinary. Whatever the verdict, the implications for planetary science and small body research are profound. 3I Atlas lets us sample, at a distance, material formed around another star. A CO2-rich coma points to different thermal histories and chemistry, expanding our models of planet formation, volatile retention, and migration. If it is indeed billions of years old, it broadens our small body census beyond the epochs that shaped our familiar comets. From an astrobiological and philosophical standpoint, the object sharpens a key question. How do we distinguish the natural for the technological in space? Should certain accelerating bodies be treated as candidate technosignatures? What thresholds would qualify? In practice, 3I Atlas will reshape survey design. Historically, small body science focused inward, main belt asteroids, Kuiper belt objects, or cloud comets. But as interstellar visitors become more common in our data, we'll need a different playbook: continuous, high-precision astrometry, real-time spectroscopy and polarimetry, and rapid triage for non-ballistic behavior. If some interstellar objects break or change vector, we must rethink mission architecture. Could we intercept one? For 3I Atlas, launching a dedicated chaser after discovery likely exceeds our current Delta-V budgets. But the larger lesson is clear: catch the next one earlier on its inbound leg, or ready high-sensitivity instruments for close monitoring. There's also a cultural inflection. A visitor exhibiting breaking ignites public imagination in ways ordinary observations seldom do. The awe of "we might not be alone" must be balanced by the discipline of test, measure, replicate, verify. 3I Atlas becomes a wake-up call for funding, for international coordination, for integrating space situational awareness with interstellar object tracking. Looking ahead, data from March 2026, when 3I Atlas passes about 0.354 Australian dollar from Jupiter on March 16th, will feed late-stage modeling. Even as the object dims and recedes, its recorded journey will sharpen our calibrations of coma evolution, dust dynamics, and non-gravitational forces. In essence, 3I Atlas stands at a crossroads between classical comet science and techno-signature inquiry, between solar system dynamics and interstellar behavior, between passive drift and purposeful motion. It urges us to revamp our ontology of wanderers, not only as natural byproducts, but as potentially engineered craft, or at least as relics of alien systems with histories unlike our own. Whether 3I Atlas proves natural or artificial, the conjunction of braking, non-gravitational acceleration, and unusual chemistry marks a pivot in human space science. We are witnessing an object that presses on our instruments, stretches our models, and reframes our expectations. The solar system is not merely a laboratory. It is a junction, and we are only beginning to learn the rules of its traffic. What remains is further observation, careful modeling, and a brave openness to possibility. As researchers continue to analyze 3I Atlas's coma, dust and gas output, tail structure, polarimetry, and trajectory residuals, we will gain not only a clearer picture of this traveler, but a richer map of the interstellar population yet to be found. If history is kind, the anomaly of 3I Atlas will become a catalyst, a single wandering object that quietly launches a century of interstellar astronomy. If this kind of calm, cinematic exploration resonates with you, like the video, subscribe, and share your thoughts. Did NASA just witness an artificial maneuver, or nature at its strangest? What do you expect next?